Hi guys, Mr. Brosnan here. Just going over a PowerPoint that's going to help you to look at acids and the properties of acids and bases. So if you look here, we've obviously covered atomic structure. Okay, so we're looking at what we're doing for the external assessment, which is aspects of acids and bases. Okay, so over this next few weeks, we should be able to cover the properties of acids and bases and potentially look at neutralization. If we go further down the track with this isolation, then we'll be looking at rates of reaction. Let's start with acids. All right, acids are obviously acidic. Okay, and it's obvious from the acids that you have at home that they are sour. Okay, these organic acids that you would have experienced are called organic acids. Now, organic acids, as you can see in the picture there, could be something like the acid from lemons, okay, or citrus fruits. So we call that citric acid. We also have acid in grapes, which is tartaric acid. We have acid in apples, which is malic acid. Acid in yogurt, which is lactic acid. Okay, and even acids in ants, which is formic acid. Okay, the mineral acids, though, what we're looking at are the acids that we find in the lab. Okay, so you see the bottle next to it there, that's got H2SO4, well, that's sulfuric. So we call that a mineral acid because it's something that's been made out of minerals. Okay, so we just move on and we look at the properties of acids. Okay, so acids, they have a pH of 7, less than 7, sorry, so therefore it would be 1 to 6. 1 would be a strong acid and 6 would be a weak acid. If we're going to test them with litmus paper, we'll turn litmus paper red, and universal indicator will go from red to yellow. Again, a strong acid would be red, okay, and a weak acid would be yellow. They're base opposites, so they'll be neutralized by bases. We'll talk a little bit about that when we look at acid-base equations. Okay, but as you can see, acids react with a whole lot of things, and all of these things below us are basically all bases, right? Bases in just different forms. So if we start with carbonates, okay, they'll react with that to form a metal salt plus water plus carbon dioxide. And then you can see there that they also react with acids, metals, okay, and they will produce, as well as a metal salt, hydrogen gas. So that's the example of the POP test that we've done in class. We also going to react with two types of bases down here, metal oxides and metal hydroxides. So the important thing to remember there is that not all bases are alkalis. Okay, the only alkalis there are these metal hydroxides that we can see. Okay, so when we look at acid-base reactions or talking about the ion concentrations, we'd be talking about the interaction with these metal hydroxides. So acids will react with metal hydroxides to form a metal salt in water. The only difference between the metal hydroxides and the oxides, well, obviously oxides are not soluble in water, okay, so they are just known as bases, but they will still produce a metal salt in water when they react with an acid. Okay, and last but not least, we've already said that acids have a sour taste. Again, just a little summary of what acids do, okay, and that's what we're looking at. Okay, if we look at primary, what we need to know about acids, okay, well, you can see there that all of these formulas have an H attached to them, okay, so that means that acids contain H plus ions, all right, the more H plus ions they have, okay, the stronger the acid, okay, so the strong acids in our labs, all right, nitric acid, see there, HNO3. If we remove that H, well then obviously we get a nitrate. So that's going to help to produce our metal salt. Nitric acid, all right, hydrochloric acid, HCl. Again, remove that H, we end up with chlorides. And then finally sulfuric acid, H2SO4. Again, if we remove the hydrogen ions, all right, then we're going to have sulfates. So what we talk about is the fact that we have an excess of H plus ions, right, when it's dissolved in water. Okay, and so our lab acids have an excess of H plus ions. These are just some common names and formula for our acids. So hydrochloric acid, we're just gone through these, okay, but we'll just talk about them again. So again, as I said, once we remove the H plus ion, it's going to contribute to turning into water. We're then left behind with chlorides. Sulfuric acid, again, we're going to produce sulfates, and then nitric acid, we're going to produce nitrates. So that's it for acids and their characteristics, basically. Okay, if we look at bases, all right, bases have a few less properties than acids. Okay, but we commonly see them in our households as cleaners. Okay, because they're very good at removing fat and oils from things. Okay, so because of these OH minus ions. All right, so basically bases are the opposite to acids. All right, and they want to remove the H plus ions from solutions, which helps to neutralize an acid. Okay, so obviously we have cleaners, which are bases. Some of them are alkalis, which makes them strong acids, and some of them are weak bases, and some of them are weak bases. We also have weak bases like antacids to fix indigestion. Okay, but the one we considered there is looking at those alkalis and the fact that these here are alkalis, right? The metal hydroxides, so they have an excess of OH minus ions dissolved into water. Okay, if we move on to the properties of bases, right? They have a pH of more than 7, so 8 to 14, and obviously 8 is a weak base, 14 is a strong base, and 14 is probably usually an alkali. If we look at how they interact with red litmus paper, they're going to turn red litmus paper blue. Okay, universal indicator is going to be going from blue to purple, and blue is going to be the weak base, and purple is going to be a strong base. Obviously, they neutralize acids, as we've already alluded to. Okay, and they feel soapy or slippery. Okay, this is because they remove the oils and fats from your skin. So that's actually what causes the slippery feeling. And then this last part here, again, as I've alluded to, is what we're concerned with when we talk about the concentration of ions in a strong base. Okay, so we're talking about the fact that an alkali has an excess of OH minus ions. All right, when the alkali becomes weaker, that excess has been reduced, so we have less concentration of those OH minus ions. Okay, and then obviously they taste bitter, turn litmus paper blue, and they're slippery to touch. So if we look at the fact that they have OH minus ions, which means they're actually able to accept H plus ions. Okay, so they're looking to get the H plus ions from acids. All right, so eventually, if we get enough of those H plus ions, it will reduce the concentration of OH minus ions, and they'll combine together to form water. So that's where the water comes from in those word equations for acid bases. And you can see there in our lab, right? Obviously, the common strong base is sodium hydroxide and other metal oxides. Okay, and we've got carbonates and hydrogen carbonates, which are also bases. So there you go, sodium hydroxide, NaOH. Okay, the OH is obviously means it's a base because it's got OH minus ions. And we've got calcium hydroxide, Ca bracket OH bracket 2. These two here, obviously carbonates, have extra oxygens attached to them, hence the fact that they produce carbon dioxide. So the bases that here include the metal oxides, okay, the metal hydroxides, metal carbonates, and hydrogen carbonates. The metal hydroxides will be the ones that you have to talk about in terms of how they react with H plus ions, and looking at the concentration of those OH minus ions. These other ones you'll have to write word equations and symbol equations to show the interaction with acids. So that's it for now in terms of the properties of acids and bases. I will send out some SciPad worksheets that you'll be able to fill out on a Word document, and you'll be able to send back, or we'll be able to fill out on Teams. So look forward to seeing you guys face to face at some point. Keep safe and see you later.